Hi, this is Mark Ceresano, RPT, and I'd like to talk to you about the pure perfect fourth. If you've been studying piano tuning at all, you have learned that the perfect fourth is wide, but I'm here to tell you that some perfect fourths are pure. Don't believe me? Keep watching. Consider the perfect fourth A3D4. Now, consider the partials above each note. Notice the coincident partials. We know the perfect fourth is wide, but did you know that when we say that, we only mean wide at 4-3? What about the 8-6? Consider this graph from Piano Meter. Notice, the 4-3 is wide, but the 8-6 is pure. What? Even if this is true, how are we supposed to tune it this way? Consider again the perfect fourth, A3D4. The 8-6 coincident partial is at F6. The test note for any interval is 2 octaves plus a major third below the coincident partial. Try to memorize that. In this case, the 8-6 check note for the perfect fourth, A3D4, is F4. This is how you test for a pure perfect fourth at 8-6. Play the test note with one interval note, listening for the beating at the coincident partial. Play the test note with the other interval note, listening for the beating at the same coincident partial. Keep alternating and comparing beat rates. The interval is pure when the beat rates are equal. How does it work? Consider the perfect fourth A3D4 again. Now look at their partials this way. Let's look at the 8-6. Now the check note is 2 octaves in the major third below the 8-6, F4. The check note also has a coincident partial at 8-6. That's why it works. But the check note, CP, is always flat of the interval CPs, like this. That means every time you play the check note with the interval note, you are measuring how sharp the interval note coincident partial is. The beat rate represents the sharpness of each note. Therefore, if the beat speeds are the same, the coincident partials are the same, and the interval is pure. Get it? Here's some oral examples. This is the perfect fourth A3D4. This is the perfect fourth A3D4 filtered at the 8-6. Notice, it's not pure. The 8-6 is beating. But is it beating wide or narrow? To answer that, we need the check note. This is the minor 6, A3F4. This is the minor third, D4F4. Are they the same speed? No, the minor third is slower, and slower means lower. In this case, D4 is slower, D4 is the top note, and top lower means narrow. This is a narrow perfect fourth at the 8-6. So now you know that some perfect fourths are pure, the 8-6. But what about chords? Can chords be pure? Yes, they can. We're going to talk about the pure minor chord. Consider this C minor chord in second inversion. Now consider the E flat as a check note. Notice the intervals it produces. A minor 6 with a coincident partial at G6. A minor third with a coincident partial at G6. Each of these intervals beat at G6. This is the key to understanding pure chords. If these intervals that share a common coincident partial are beating and they beat at different speeds, then that beat will beat at the coincident partial. This chord is not pure. Hopefully the following example will help. Remember this? Here are the interval notes and the check note. This is a D minor chord in second inversion, made up of these two intervals that beat at A6. But if they do not beat at the same speed, then the beat will beat and the chord is not pure. This is the minor 6, filtered at the partial, plus the minor third, filtered at the partial. These are not the same speed. Therefore, the minor chord will have a beat that's beating. Therefore, the chord is not pure. Well, what about a pure minor chord? What does it sound like? Check out this minor chord. It has these intervals, the minor 6, beating at the partial, and the minor third, beating at the same partial. And they beat the same speed, which means The beat doesn't beat. This is what a pure minor chord sounds like. This is not a pure minor chord. Pure fourths and pure minor chords, only taught at the International Piano Technician School.